first speaker, so I will start immediately. And I'm from Denmark, I'm going to talk about voids in ductile solids in situations where the stress triaxiality is 0 or near 0. In previous years, I've been looking at a number of works at situations where a number of voids, like such a row of voids, is subjected to situations near simple shear. That means they are subjected here to tension and to shear. And then periodicity conditions are used between cells. This is an example of the results obtained. If you look at the ratio here is sigma 2 is 0, so here we have simple shear, and here we even have compression. And the interesting thing in these previous results is that a maximum shear stress is actually reached. That means the voids explain final failure, even though the voids at the stage over here collapse to microcracks. And from that on, they are microcracks, but they still, by interaction with neighboring voids, give a failure by maximum stress. Now, to look at another situation with small stress triaxiality called pure shear. This is a situation where you have here tension in this direction and compression in this direction. If the compression true stresses are equal to those in tension, then it is pure shear. And that means there's 0 stress triaxiality. This is really a unit cell representing a number of a periodic pattern of voids. The kind of results that come out of this for if this ratio, let's see, if this ratio is equal to 0, this is pure shear. You see that what happens is that the voids become microcracks, they grow completely into microcracks, and there's no tendency of failure at all found here. Various things were investigated, but it was not possible to find a mechanism like that in simple shear, where the voids would explain failure in this study. Here you see a situation where such two voids that were initially of equal size, they are collapsing. Here they have collapsed completely. You see there's complete contact and the material is just elongating. The same situation where you see the strains. You see that there is some interaction between the two voids, but afterwards this is just remains of that interaction, and the remaining stretching doesn't show any sign of a failure. So this was the reason for looking into the study that I shall present now briefly in the remaining part of the time. A study where if we make this less perfect, if we include an imperfection, and in this case the imperfection will be included as a sheet of voids. You see here, this represents a number of voids inclined relative to the tensile direction. The inclination I shall mainly use here is 30 degrees for that initial angle. The study is made so that the material outside is, for example, exactly in pure shear. That means that there's a compressive true stress that's equal to the tensile true stress out there. Then on the boundary here, the compatibility with that strain state and stress state is prescribed exactly. On the sides, there are periodicity conditions, and that means this imperfection is made in order to see if, even though the previous study didn't show a failure, if this skew line of voids would trigger a localization. We could think of a failure by localization in pure shear. So that's the idea. And okay. And the mathematics of these equations, finite strain and so on, I don't need to talk about those because they are as I explained. So here's a mesh used for this situation. Of course, due to the boundary conditions, we must expect that in the region, the outer region of this unit cell, we will have stress and strain states that become exactly the same as those at infinity. Also because we only have this one row of voids. This is plane strain, by the way. It's a plane strain approximation. Because we only have this one row of voids, the void volume fraction in the whole solid is 0. There is only one row of voids in an infinite solid. So here's a result for a case where the initial radius over half spacing is 0.175. The aspect ratio of the unit cell that I just showed you is 2. That means it is 2 times as high as its y. And the stress ratio outside is kappa. This means that here at 1 we have pure shear. At 0 we have no transverse stresses, so that is uniaxial plane strain tension in the up-down direction. It's not so clear here, but for these end at being completely horizontal, and that means that we actually, in these 3 upper curves, we end up seeing a localization. This void sheet develops into a shear band where failure will happen in a so-called void sheet. But that does not happen here, as you cannot see very clearly here, but we'll see on the next slides. What you see here is the angle of the angle phi indicates the angle. Initially it's a round void, so there's no angle, but this void quickly starts to collapse, and then there is an orientation of the void, which initially becomes something very near to 90 degrees. That means the void stands up down, but you see that for example, in the cases of uniaxial plane strain tension, you see that it lays down more and more in the shear band that's developing along these skew voids. A shear band develops inside the unit cells, and at the same time that void rotates. That also happens in these 2 cases. These 3 cases are those where we actually find a localization. In these cases, what happens here is just around this point, the void collapses to a microcrack. At that time, it turns out that the process towards localization stops. They start to rotate backwards. You see it's clear on these 2 curves. That one is for pure shear. And the third curve here is about to do that. It has just had contact, but will do that later in the curves here. This is the most clear picture because this shows the behavior of the same curves in a situation where what we plot is the average logarithmic strain inside the unit cell in the 2 direction divided by the logarithmic strain outside, out at infinity. And there you clearly see that in these 3 cases the straining outside stops and the straining inside the unit cell becomes very large. So it's quite clear that inside that unit cell, and that's around the voids, there is a localization. But the conclusion that we were really looking for here is, would something like that happen in, in pure shear? It will not, according to this, it will still not happen. So the imperfection is not important enough to make such a failure in pure shear. And basically that's the conclusion of this study, that it has still not, even with this, been possible to find a mechanism that in pure shear, where failure is predicted due to the voids, it would have to be due to something else, but not due to the voids. They do not do that. Let's see. Here's one of the cases. It's still for pure shear. You see that the initially round voids have here collapsed towards a microcrack. Here it has become a microcrack. There is a width, but that's because of a pseudo method for making the contact. The rather strong contact develops here, and you see clearly that the void has rotated a little. It's rotated in this direction. That means phi has gone from 90 degrees to a smaller value, and is still going smaller here where there's contact has just started. And the next slide let's see. No, that's not the next. Yep. Oh, that one. You can, if you just look back at this case and then look at the next case, you can see that it has rotated back. The fact that it stops rotating but rotates back is clear in these pictures. There's still some sign of localized straining here, but it hasn't grown. It has stopped. That means you see that in the way that the difference between the strains here and the strains outside have not increased. Here's maybe that's the last slide I should show, because the other slides just show that it does the same. But this is interesting in a way that the unit cells I have shown so far had the aspect ratio of 2. If you make the aspect ratio 4, that means it is 4 times as high as is wide. Then you should find the same result exactly, because the whole idea is that the boundary conditions are against the solid at infinity, and this really shows that they are nearly the same. That means that the aspect ratio 2 is maybe not quite large enough to make it independent, but it definitely will become completely independent when the aspect ratio of the unit cell then grows. Then a large part of the unit cell will have stresses and strains that are identical to those outside. I think it's time I should stop now. Since I'm also the chair, I should ask if there are any questions.